second part of the talk.
Right. Thanks. Thanks very much. Thanks to the organizers for arranging this filler. Okay. Let's see. So Parthanil finished this talk. We've taken out the little bit that we'll need where he concluded. So we are looking at partial maxima of random variables indexed by a group. And if the partial maxima suitably normalized converges to a non-zero random variable, we'll say that it's IID-like. And the investigation is to find examples, to find natural examples where this kind of behavior does occur. Yeah? And towards the end, he looked at the action of FD acting on boundary FD equipped with a measure mu, where the mu was described differently, but since we've heard this already in the previous week, mu is the Patterson-Sullivan measure on the boundary. Okay, so, pardon me? Could you just say that? Oh, yeah, sure. So, you want me to say what the Patterson-Sullivan measure is? Okay, let's see. So, what do you do? So, you look at, so I'll define it in a slightly more general context. We will come to that. Okay, so here's sort of the general abstract setup in which we're doing this is triples. So you have XD. This is, let's say it's a geodesic metric space. And from now on, gamma is going to become lambda, okay, for a particular reason. So lambda mu, this is a probability measure space. G is a finitely generated group. And so you have essentially these triples, X, lambda, G. This is a triple. And what do you want to do? You want to look at, so one particular simplifying assumption that we've used is that function Fe, which was obtained via the Rosinski representation, this Fe is identically 1 in the previous lecture, which essentially means that we need to look at so far, it's just a probability measure on lambda. And what is the action of G? G acts on X by isometries freely, properly discontinuously. So this expression, by isometries, free, properly discontinuous, this is sometimes abbreviated to say the geometric action. So it's a geometric action on some space, and the action on lambda, mu, this is a quasi-invariant action. All right? So far, there is no relationship between the geometry on the one hand, xd on the one hand, and the measure space, the probability measure space, the G action on the probability measure space, right? So what are we really looking at? We are looking at max. So this is Mn, this is the max as for G belonging to Bn, and the meaning of this Bn is going to change a little bit. D mu composed phi G d mu at a point X, and then integrate this out over lambda d mu X. Okay? So this was our Radon-Nikodym cocycle or derivative, and you're integrating this out with respect to the measure that you have, and you're extracting. No, I just want to do this. So I want to find an alpha independent. I want to find the alpha independent term. Okay. So I'm looking at just the cocycle. Take a point x on the boundary. Evaluate the maximum of the cocycle while g varies over Bn. In the previous talk, capital B sub n was the collection of g such that g belongs to the n ball in the Cayley graph. Yeah? But now we have introduced some general space, x, on which the action is geometric. So now the meaning of Bn is the following. So x comma d is equipped with a base point, let's say O, and now Bn is equal to g belonging to g, such that g dot O belongs to the n ball about O in the metric on x. Okay? So basically the collection of points, collection of elements of G over which you're taking the partial maxima, that's getting controlled by the space on which the group G is acting geometrically. Okay? So in particular, when capital X is also the Cayley graph, this Bn and the Bn in the previous lecture coincide. But we want a more general setup where G is allowed to act on some auxiliary metric space. Okay. So far, again, let me just reiterate, there's no relationship between, except here, I mean this Bn and this measure space lambda. A priori, they have no relationship. Yeah? So now we'll have to, so the next step, specialization, specialize to lambda is, let's say, is the limit set, okay, of G action on X. What does that mean? So let's see. Let us specialize further. This is not, I mean, this is an extra hypothesis which we'll introduce right now. Maybe if we have time right towards the end of the lecture, we'll relax this. But suppose X is Gromov hyperbolic, proper, and we actually use some uniform properness. So G acts on X. Then we saw from Peter's lectures last time that boundary X, this is the Gromov boundary of X, and if you adjoin this boundary of X to X, natural compactification because X is proper. So lambda is equal to the collection of accumulation points of G dot O, this collection, G varies over capital G in boundary of X. Okay? So lambda is also called the limit set. So far it's just a limit set of G action on X. Fact is that lambda is independent of base point O. All right, so now we have various entries in our, various players of the game have been identified. X is a Gromov hyperbolic space. G is an action, G is a group acting geometrically on this. Lambda contained in the boundary is this limit set. What about mu? So mu is a quasi-conformal density. What does that mean? So dimension some v. This little v is the little v that occurred in Peter's talks last time. So what does that mean? So far, it has no significance. But what does it mean to say that mu is a quasi-conformal density of dimension v, i.e. distance, the Radon-Nikodym derivative d mu compose phi g d mu is equal to e power minus v that evaluated at some xi, or did I write x? Oh, I wrote x, okay. So let's write x. This is equal to e power minus v beta sub x O g dot O. Okay? So O is our base point. Yeah? This is really all you'll need to know about the Patterson-Sullivan measure. Okay? So this is a conformal density, and this equality, I mean, thanks to my wonderful handwriting, you can't distinguish between that and it's approximately equal to, which really means that this is equal to up to multiplicative, up to a multiplicative constant in 1 by c for some c greater than equal to 1. So if c equal to 1, then this approximate equal to becomes a genuine equal to, and then it's a conformal measure, a conformal density. And if it's some constant, yeah, which will be uniform for the problem that we are looking at, then it's called a quasi-conformal density. Okay? So that's all we are really looking at. Okay. Any actions? Yeah. So we'll come to. I mean, that's a. So I hope to answer that question towards. I mean, as we progress into the talk. Yeah. Because, I mean, it's much easier to say that this is a quasi-conformal density and say appeal to Patterson-Sullivan to say that such objects exist, yeah? in the context that we are looking at, rather than trying to construct them by hand. Yeah? The construction is very explicit, and you can do it by hand, but it will take a lot more time. It's better to just sort of take this as the black box and that things exist. So there's a theorem. This is Patterson and Sullivan QC densities exist in this context. Which means what's the context? Group G acting geometrically on a hyperbolic space, and the measure is on the limit set. And oops, I should also say coordinate. So it's in the form of hyperbolic setup, it's really coordinate. I mean, okay, so in terms of attribution, in the H2 case, hyperbolic plane case, it's due to Patterson. Hyperbolic n greater than equal to 3 is due to Sullivan, and general Gromov hyperbolic is due to coordinate. Pardon me? That is correct. That is correct. Okay. Yeah. Okay. In fact, Coordinate's work appeared in Pacific Journal, which is actually sort of for good exposition. So it's all right. So these quasi-conformal densities, these QC densities, are also called Patterson-Sullivan densities, or sometimes a misnomer measures. So they're really measure classes, not measures. Okay.
They are measures, actually.
Okay, I mean, yeah, so I would say that the whole collection is a Patterson-Sullivan density. I mean, one for every base point. So yeah, I mean, depends on what the context is. One of them is a misnomer, the other is, okay, all right, so this is really what we'll be requiring, yeah? So now, with this, I mean, so from Patterson-Sullivan theory, all that you really need is this particular formula, okay? So what are we really looking at? So therefore, Mn was the maxima of stable random variables, symmetric stationary, symmetric alpha stable, stationary random variables. Stationary should be at the beginning. What were we really looking at? We were looking at, yeah? Oh, Mn was maximum. So this is something that we'll be looking at. This is some An. This guy at a point was what you were calling Mn? Oh, Mn was the maximum of the random variable via the Rosinski representation. This is what we were looking at. Okay. Okay, fine. So we look at a deterministic quantity, maximum, G belonging to Bn. Oh, I forgot to say what little v was. So before I get on with this, what is v? And you've seen this in Peter's talks last time. What about the dimension v? So the dimension v has occurred at least twice. I have 2 sets of lectures last week as the topological entropy. So this is equal to limit as n tends to infinity log mod Bn by n. Okay? So this occurred in Lin-Shu's talks in a smooth manifold setup, and it also occurred in just talks in the discrete setup. No?
Then what is Bn?
No, so Bn is, so this n, so what are you looking at? So Bn is the G such that G dot O belongs to ball of radius n about the base point. This is contained in the space X. Metric on the ambient space. So this ball of radius n about O is in the metric of the ambient space. Yeah. So this is equal to, I think, volume or topological entropy. And so there's a crucial difference between the abelian and the non-amenable case here, really the hyperbolic case. You look at, I mean, the normalizing factor in the abelian case, z to the d, was really n to the d. Yeah? Here, normalizing factor, so normalizing factor, which was this mn by mod bn to the 1 alpha. Yeah? Since our alpha is 1, I mean, we've assumed alpha equal to 1 here. This is equal to e power bn. So this is the exponential volume growth or volume growth of x, actually. Well, yeah, of, let us say, CH of lambda contained in X. So what is CH lambda? I'll have to say a little more about this. So there is some redundant part of X where nothing happens. So what are we doing here? What is CH of lambda? This is equal to union over psi, O is our base point, xi, geodesic rays. This, okay, so it's the union of all these guys, where xi belongs to the limit set. So basically what you're doing is you're constructing a convex or a quasi-convex subset of the hyperbolic space wherein all the action really lies, okay? And, pardon me? It depends on the choice of the base point, but e power Vn, this is really equal to, okay, so I've written this here, e power Vn is really equal to the exponential volume growth of the convex hull of the limit set, because that's really where the action exists. So you can take the space and take a free product with z, and that extra factor is not going to play any role. So really, the action is here, and it's the volume growth of this guy which is important. What about Mn? What about, let's say, An? This was, okay, so I've erased that. And this was now again G belonging to Bn. Look at e power minus V, beta x, O, G dot O. So what is the object that we are looking at? It's An, and this normalizing factor, let's call this Vn. So An by Vn, this is equal to, okay, An was actually d mu x integral over lambda. So this is equal to, so 1 by e power Vn integral over lambda max G belonging to Bn e power minus V Busemann function O G dot O d mu x. Okay, this is the object that we want to look at, and here is the fact that we are taking out of the probability that asymptotics of Mn normalized is determined by the asymptotics of Cn subject. All right. So what does that mean? What does this asymptotics of Mn is determined by asymptotics of Cn mean? So now we'll make a definition. And one more term. Yeah, so Patterson-Sullivan, stable random fields occurred in the previous talk. Patterson-Sullivan has already occurred, but we'll now have to say what extremal cocycle proof is and define that. So definition, if lim inf n tends to infinity of Cn is greater than 0, then we say that x lambda g with the extra pieces of decoration, distance and measure, has non-vanishing ECG, extremal cocycle growth. Note that, yeah, so this is one. And second, if the actual limit n tends to infinity, Cn is equal to 0, then x lambda g as vanishing ECG. Note that after having chosen our Fe to be identically equal to 1, now the randomness has completely gone out of the picture. Yeah? So how do we connect this back? And essentially, that Parthenil was alluding to in his work, essentially the same work and same thing. This is Samorodnitsky. Essentially, I mean, the same ideas. You can basically say that ECG greater than 0 implies that XG has IID-like behavior with respect to partial maxima. Okay? So really, our point now is to determine this object, the asymptotics of Cn. Yeah? Pardon me? So the point is, as soon as you take f to be equal to 1, the dependence on alpha goes away. Really what we are doing is, maybe I won't have time to come to it, so I might as well say it now. What we are really looking at, I mean, I'm not very sure, but I think what we are really looking at is f belonging to the intersection of all L alpha, alpha ranging between 0 and 2. So essentially things which are bounded functions. So therefore the behavior for this is to be taken with depending on taste, how much salt, yeah? But essentially, I mean, the behavior of a constant function should determine functions which are bounded both away from 0 and infinity. And so this part we haven't yet completely thrashed out, but most likely that's the case. Pardon me? Yeah, so ECG equal to 0 implies XG normalized, Mn normalized goes to 0. That is correct. That is correct. That is correct. So I think, so there is no proper definition of IID-like. Yeah? So we define IID-like as up to subsequence. Yeah? Okay. So let's see. So now we'll have to do this computation. So what is the behavior of this cocycle as n tends to infinity? That's what we need. So what is C? Yeah? All right. So approximation strategy. So instead of computing, so what we have, so again, this is supposed to be our x, thought of as a ball. You have your point at infinity. I think I must have called it xi somewhere and x somewhere else. Oh, I still consider, okay. So there's little x here. And you have a collection of orbit points. So what do you want to do? You look at, so here's your base point O. You take an n ball about O. And now what do you want to do? You want to look at, so you join x to O. There is some point at which this point is called the projection of x onto the boundary of the n ball. Yeah? So what you really want to do is you want to compute the extreme value of the cocycle as g varies over this ball of radius n at a point x. What do we want to do? So instead of computing it with respect to the Patterson-Sullivan measure on the boundary, we want to compute it with respect to an approximating measure in the interior. Yeah? So assume, let's say, so this picture is boundary x is equal to lambda. So if boundary of x is not equal to the limit set, we just take the convex hull of the limit set to be x, to everything there. Okay, so need approximating measures mu r. Okay, so this is mu sub n. So what is the measure on the ball which approximates the boundary measure? And here's the point. Mu n, for the case of Patterson-Sullivan, mu n you can take to be the uniform measure, assuming this is some uniform graph, you can take this to be the uniform measure on Sn, which is equal to x belonging to x, such that distance between O and x is exactly equal to n. So I have not said exactly what the structure is, but I'm assuming that this is some uniform space, yeah, on which uniform measure makes sense. All right. So for example, if you won't be far wrong, if you think of this as, so what are these really? So, okay, so in order to define this, I'll just say the words, I won't get into this. So that in a general hyperbolic space, the tangent space, there is no real, this is some discrete object, right? However, you can make a measurable model for, so lambda, so there's a measurable model. So basically what I'm trying to get at is what does this uniform measure on Sn mean? So measurable model, you can, okay, maybe I'll come to that later. Yeah, no. So measurable model is take lambda, the limit set, cross it with itself, remove from that the big diagonal, okay? So basically you take pairs of distinct points, x comma y, on lambda, and take a product of this with r, okay? This is the measurable model for the unit tangent bundle to the CH of lambda mod group G, and then take its universal cover. Yeah? So you saw this kind of thing in Lynn's talk last time, where you were really looking at a manifold, a compact manifold downstairs, yeah? But the compactness of the manifold did not really play a role. You could take a manifold, and then what you're doing is, you were really passing to the universal cover. The universal cover was CH, yeah? Is replaced by the convex hull here. And we want to have a tangent space, a replacement of the unit tangent sphere, and that's taken over by the limit set here. Okay. All right, so this object is denoted as lambda 2, lambda cross lambda minus this is denoted as lambda 2. So lambda 2 cross r mod G, this is what we'll call the unit tangent. This is the measurable unit tangent bundle to some manifold M. And what is the manifold M? It's just, you think of it as coarsely as just the convex hull quotiented out by the group G. Okay. So now what are the uniform measures? What are the approximating measures? Once we have this extra r direction, so this extra r direction gives direction of geodesic flow. Okay, and what is it? So mu sub n, this is equal to the Patterson-Sullivan on lambda thought of as the tangent space to M at the base point O, put forward by geodesic flow through time n. Okay? So this is really, so what is all this? This is some general nonsense. What is really happening is that, think of this as a negatively curved manifold, smooth negatively curved manifold. Then on the unit tangent sphere at a point, you can naturally attribute via the exponential map the Patterson-Sullivan measure at infinity. Yeah? You are equipping the unit tangent sphere to O with that measure. Yeah? Now flow through time n. Yeah? As a result, and then exponentiate, you're going to get approximating measure mu sub n on the collection of points at distance exactly equal to n from the base point. That's our approximating measure. Okay, so now what do we want to do? We had this Busemann function that we wanted to evaluate. There's something special that happens because of negative curvature. So e power minus x o g dot max g belonging to Bn. Again, this is approximately equal to, up to some, again, some uniform multiplicative constant, which will depend only on the problem. This is going to be equal to approximately e power minus v distance between little o and, what do we want to do? Oh, this is the distance between pi sub nx and g dot o intersect bn. Okay, so what are we doing here? We are taking this computation of a cocycle at a boundary point, we are bringing it in. So we really want to compute for this point, this is pi n x. For this point, we want to compute the same quantity. Okay? Now, you have any, so for, you have, say, suppose some g dot o here. What do you want to compute? You want to look at the maximum value of this guy. Yeah? Which means what? Which means you want to look at distance of this point from any orbit here. So here's a certain fact of negative curvature that we are using. If you take this, take the geodesic from pi n of x to x, so from x to pi n of x, and follow it up by a geodesic which goes from here to g dot o. Yeah? So this is, yeah? Oh, this is probably plus. Is it? If it is close to the orbit, then. Yeah. E power distance between pi n of x. You have, if it's close to the orbit, then this is bounded. This is zero, yeah.
So exponential is 1.
It 1, yeah.
On the left, you have exponential dn. So you need only just exponential dn times this.
This divided by 1 by e power dn. That's correct. Thank you. Yeah, this is a normalized object. Yeah, absolutely correct. Thank you. So what's the, so this is 1 by bn. This is the normalized object that we are computing. Okay, so if you have any point inside this ball of radius n, then you take x, 2 pi n x, the geodesic ray, follow it up by a geodesic which connects this to any point inside the ball. Yeah? Then this followed by this geodesic is within a bounded, uniformly bounded distance of the corresponding Busemann function, x to g dot O. Okay? So essentially, this is what allows you. So that extra distance is, once you exponentiate it, that gets absorbed into this approximate equality. So this is really what we want to evaluate. Yeah? However, there is a little irritation here. You're not really looking at the distance of a point pi n of x from the whole orbit, but you're looking at the distance from the orbit intersect the ball of radius n. Okay, so I think 13 minutes, but I want to put another approximate equality here, and this is approximately equal to d pi n x, just g dot O. There's one more property of the Patterson-Sullivan measure that I'll be using here. Yeah? So this is, so I'll try to justify this approximation if I have time at the end. Yeah? But now it becomes a fairly nice object. So what do we really want to do now? What are we doing now? So now you have Sn of O. This is a sphere of radius n about the base point O belonging to capital X. And what are we doing? Integral over Sno with respect to the approximating measure, but now x belongs to the sphere, distance between x and g dot O. This is what we want to approximate. So want to estimate. So to estimate this guy. Okay, so far no further assumptions have been used. And now I'll come back to, pardon me? That is correct. By e power. Oh, yeah. E power exponential minus v, this guy. That's correct. So this is what we want to estimate. So far now I'll come back to two questions. One due to Vadim towards the end of last talk is, have we been using, so two things. So one is this is what Sebastian was asking, special properties of the G action are we using? First question. Second question is ergodicity related issues. What are these? Okay. So, and I'll try to address these two questions simultaneously. And here is precisely where the analysis will bifurcate. Yeah. So two cases. One, I don't think I'll have time to define the Bowen-Margulis measure. It was defined last week, so I'll just cannibalize that. So mu Bowen-Margulis of the measurable unit tangent bundle less than infinity, or the other case is both m is equal to infinity. Yeah? And in our setup, I think what Sebastian was calling wild is essentially this. Is this what you had in mind? So this is not quite geometrically finite, but sufficiently close. Yeah? All right. So there's this dichotomy. So let's do so what does this have to do with what we started off with? And this dichotomy exactly dictates for us what we want. So here's the theorem. Mu bm to m equal to infinity implies ECG vanishes. And second, the Bowen modulus measure is finite, implies that ECG is non-vanishing. So, and the proofs are somewhat different. So the proof of one, essentially, it relies very heavily that the theorem due to Roblin, which basically says that here mod Bn, this implies that mod Bn is little o of e power Vn. Okay? So that means this mod Bn by e power Vn goes to 0, then tends to infinity. Okay. So here a picture, it basically says that if you look at the ball of radius n, the g orbit is very sparse. Yeah? And this implies the same thing as that if you look at the C neighborhood of Bn, okay, so Bn is g dot O. Yeah, so let's look at g dot O, g belonging to Bn. Yeah? So you look at the neighborhood of the orbit, yeah, for some fixed c. Yeah? This guy is also little o of e power Vn. Why? Because if you fix your c, yeah, the number of points, if you discretize the space, the number of points in a c neighborhood is going to be bounded, assuming that the space is uniform. So the c neighborhood of the capital G orbit is also very sparse. So what does this mean? So this implies that the integral over Sn, this splits up Sn minus the c orbit of, the c neighborhood of the G orbit restricted to Bn. What's the value of the function there? Every point is at distance at least c, right? So if you look at the integrand, this is something like e power minus Vc. This is going to be less than equal to, yeah, plus some little o of e power Pn, yeah, for all c. Yeah? And just remove this. Yeah? And integrating this constant function over a larger set. So this goes to, this is less than equal to e power minus Vc with, say, let's multiply by some for all c as n tends to infinity. So this is less than equal to 2 e power minus V times c, where c was arbitrary, but c you can take to be arbitrarily large. This implies that. This furnishes the first conclusion. So what are we doing here? We are taking the sphere, we are splitting it into two parts. One part which is close to the G orbit, one part which is more than c away. The part on which it is more than c away, the integrand is very small, e power minus Vc. So there the integral is small. And on the rest, because of Roblin's theorem, the integrand is bounded. So this tends to 0. So that's the first part. What about the second part? And this is really where ergodicity, I should say some hypothesis. So this extra hypothesis that we'll introduce now is, it holds without that hypothesis, the suitable case, but we'll say what the hypothesis is. So the hypothesis is that so far, we have assumed that x is just Gromov hyperbolic. Yeah? So x is now a special kind of Gromov hyperbolicity. You don't quite need this, but you need some form of this. So assume that x is cat minus 1, and x is not a tree with edges in CZ. Yeah? This is what's called arithmetic length spectrum. Yeah? So if you have these hypotheses extra, what does it give you? And this is where we'll answer Vatim's question. So with these hypotheses, this implies that the geodesic flow is mixing. So there's a very strong form of ergodicity that's being used here. And this is Roblin, and there's a stronger version due to Ricks. And what does mixing the geodesic flow give? This implies that spherical averages converge to space average. I'll say what this means, but this is just some t-shirt version of what you should be thinking in terms of. This is due to, the original version was due to Eskin-McMullen, and the version that we are really using is due to Ambroise Michel, Parkkonen, Paulin. What does it say? It basically says that you had these S and O. So what does that last statement mean? So really this is essentially the fact that geodesic flow is mixing. But what does this statement that spherical averages converge mean? It means that look at S and O and let P be the map from, let's say, X tilde, X, M. Okay, so M was equal to, let us say, h of lambda mod gamma. Okay, so Sn of O was a sphere in capital X. Look at P of Sn O, and this is a projection. Oh, P will be confused with probability. Let us say capital Pi of Sn of O, and you look at X belonging to Sn of O such that pi of X, distance of pi of X from pi of O is less than equal to some constant K. This is, I'll call it as S N K O mod gamma. Okay, so Sn of O, pi of Sn of O. Okay, so basically what you're looking at is the collection of points on the sphere of radius n, which lands within a bounded distance of your base point after being projected down to the quotient manifold. And what is the spherical averages? So spherical averages converge. What does this statement mean precisely? This is the statement saying that the measure, the nth approximating measure of SNKO divided by the whole measure of SNKO, which we have normalized to be 1. Yeah? This is equal to the measure, let's say, let's call this the measure nu, of the quotient manifold M of y such that distance of y from projection of O is less than equal to k. Of this set divided by nu m of m. Okay? So essentially you have this compact set downstairs, normalize the measure of the manifold downstairs so that it has mass 1. So you look at the collection of points which land within k, yeah? And that set, the normalized measure of that is approximately equal to, okay, this tends to this as n tends to infinity. So you look at the spheres upstairs, look at the fraction of the spheres which land within some bounded distance. Yeah? That the proportion of points in the sphere which land within a bounded distance k downstairs is equal to the measure of the k neighborhood around the base point in the quotient manifold. Yeah? So it's somehow the spheres quotiented down mix in a very nice way. Yeah? So that's, and it really follows from geodesic mixing. Okay, so that really gives it. So if you have this, then it means that there is a definite proportion of the sphere, namely SFKO, which lies within a bounded distance of the G orbit. So this implies that Cn is greater than equal to, this measure is greater than equal to, so this measure is some greater than equal to some epsilon naught on k. So this guy is greater than equal to epsilon naught. And what's the value of the normalized cycle? It is e power minus k. And I forget the rest of the terms. Yeah? So I choose a fixed k greater than 0 such that the k neighborhood of the base point has some positive measure. Yeah? Work for any k in a smooth manifold. For the discrete case, you have to be a little careful, not too much. So basically it means that on that collection of points, the distance of any point on the sphere from an orbit point is at most k. So the value of the cocycle is going to be greater than equal to e power minus kv, integrated over the part of the sphere which lands in the k neighborhood. But the part of the sphere that lands in the k neighborhood has some definite mass bounded away from 0. So Cn is going to be bounded away from 0 for all n sufficiently large. This implies lim bar is greater than 0. Okay. So that's a quick summary of the two things. Okay. So I won't write because I'm supposed to be writing, but we have used negative curvature in some way, yeah? But I want to say that so long as your space has some kind of quasi-conformal density on the boundary, this really works. So for example, there are two cases which I would have liked to mention, don't mention. One is, suppose you have a high rank symmetric space. So there are two notions of Patterson-Sullivan measures on the boundary. One is due to Albuquerque, the other is due to Jean-François. Yeah? No? Okay, all right. All right, so we are using the version that's due to Albuquerque, yeah? And the measure is concentrated on what's called the Furstenberg boundary. Yeah? So you take the barycenter of a Weyl chamber at infinity, look at its orbit. Yeah? So that's the most regular orbit in the visual boundary of a symmetric space of higher rank, and the Patterson-Sullivan measure is concentrated on that. What did we use here? We used a strong form of ergodicity in the sense that spherical averages converge, which really boils down to mixing of the geodesic flow. Yeah? So there's a version which is due in various forms. I mean, I think it's due to Margulis, some co-authors, and Jaidev did the last bit. And essentially, the same kind of mixing estimates hold, and you can push through this IID-like behavior even in that case. Finally, the last example is you look at, so this is in the case of, okay, so this is, what is gamma? Gamma is a lattice. Gamma is a lattice, uniform or non-uniform lattice in a higher rank symmetric space. Again, whenever people in dynamics see this kind of thing, the immediate temptation is to translate this to the action of the mapping class group on Teichmuller space, and the same thing holds. There, it's the Thurston measure on the boundary of Teichmuller space, and these co-cycles become essentially square root of extremal length of foliation divided by extreme length of the foliation in another metric. And again, you basically have a conformal measure there, and you can do this. So what's the moral of the story? Anytime you see a conformal or quasi-conformal measure, second, the quotient should have finite volume in some reasonable sense. You would have IID-like behavior of the corresponding random. Okay, I'll stop. Thank you.
Questions?
Yeah.
The original problem was formulated just in terms of the boundary action. Then somehow you were obliged to
Square of the boundary action. That is correct. That is correct.
now, is there any way to interpret results just in terms of the original action?
Okay. So this is a question I wanted to ask the audience because, all right. Okay. So here's the thing. I mean, there is something that we have purposely, without really understanding, called IID-like. Yeah. Now, mixing of the geodesic flow is also some kind of independence, asymptotic independence of events. Yeah. So, is there a deeper connection? I mean, is asymptotic independence in terms of this deterministic dynamical system, namely the geodesic flow, and the IID-like behavior of partial maxima, is there a more intimate connection? And I think if one can excavate that and actually come up with something, then maybe one will have a better answer to your question. So as of now, I don't know.
Other questions? All right, if not, let's thank Mahan.